a lot with numerical modeling, and then Laplace transform. Yeah, I did post one YouTube on molecular modeling, as we have recorded earlier, and then we have moved to transfer functions, as well as a recording on a transfer function on YouTube, and then last week we have discussed feedback control systems. Yeah, so for today's class, we will look into dynamic control systems, where we will look into in more detail what's actually feedback control systems. Yeah? So I click this one here, dynamic control systems. Okay, can you see the PowerPoint, chapter 11? Okay, good. So if I can start my lecture now, yeah? So we look now into dynamic behavior of closed loop control systems. Yeah? As I've learned about feedback control system before, which is closed loop control systems. So now we're looking into a bigger picture of a control systems. And for this control system, which is by itself is an integrated control system, which comprise many elements. Yeah, instrumentations, as well as the actuator, the controller, and because they are um, con consisted of many elements, in this case control as well as instrumentations. The elements actually, when they interact with each other, either through in series or in parallel, yeah, we consider them as dynamics. Yeah, so in this lecture we look into the dynamic behavior of such closed loop feedback control systems. Yeah, so if you look into an examples of a block diagram, yeah, this is a standard block diagram of a feedback control systems, where we have um, the, the y set point here. We set the measurement at a particular set point, and then probably we have one instrument to measure it. Yeah, and then from there we get another um, instruments, or maybe control systems. Yeah, with its transfer functions of GC, and probably another one with another transfer functions GV, and another one maybe GP. Yeah, and then that is being controlled with like a valve with its transfer functions GV. Yeah, and then the difference between um, the YU here with the YSP here become the feedback for this system again. Yeah. So for that measurement, we have another transfer function GM in this case. Yeah? So this is an example of a feedback system. So this is the block diagram of that particular feedback control system. Let us look into an example of a stirred tank blending process, which we have discussed many times in the previous lecture. Yeah? If you remember, this is method number 2, I think, in terms of this feedback control system, where the fluid coming in with the quantity and concentration like x1 and w1, and then the other and come out with x and w here, yeah, the output, and then this is third thing that the other liquid x2 and w2 also coming in, and it being controlled with this valve, yeah, and um, and based on the signals given by the measurements, the instruments measurement here with regards to its perhaps maybe the level or maybe the concentrations inside this tank. Yeah. So in doing that, yeah, we need to develop a transfer functions for each of the 5 elements in the fluid. Here, yeah. So how many elements? 1, 2, 3, 4, 5. Yeah. For the sake of simplicity, we consider the flow rate W1, which is this one here, W1 here, is assumed to be constant, and the system is initially operating at the nominal steady rate. Yeah. So when you look at the process in the previous chapter 4, the approximate dynamic model of a stirred tank blending system was developed given by these equations here. So x asterisk s is the transfer function to k1 over tau s plus 1 k1 dash s plus k2 over tau s plus 1 w2 dash s, yeah, where the tau is equal to v rho over w bar and k1 equal to w1 bar over w bar, yeah, and k2 here equal to 1 minus x bar over w bar. Yeah. So this is how this is what is actually we are looking at for this particular point here, x1 and w1 that going into the tank here, in the blending tank here. Yeah. So we have x1 asterisk s as a mass fraction over the mass flow rate w2 dash s in terms of kilogram per minute. Yeah. For the transfer function here, k1 over tau s plus 1, and for this one here w2 is a k2 over tau s plus 1. So in this one, we have x dash ds and x dash us in sum up here, because they are in parallel. So in parallel, the transfer functions will be sum up. Yeah. So it become x1s, the mass fractions. Yeah. So this is the block diagram of the process, and decimal x bar dash sp in the term of T denotes the internal set point composition expressed as an equivalent electrical current signal. Yeah? So the x bar dash SVT is related to the actual composition set point x dash SVT by the composition sensor transmitter gain Km. Yeah? So in this case, x bar dash SVT equal to Kmx SPT 11.7, and the current to pressure IP transducer transfer functions. The transducer transfer functions merely consist of a steady state gain KIP. So PT-S over P-S equal to KIP. That's for the current to pressure transducer. Yeah. And then for control valve, as discussed last week in section 9.2, control valves are usually designed so that the flow rate through the valve is a nearly linear function of the signal to the valve actuator. So therefore, a first-order transfer function is an adequate model, which is given by this equation W2-S over PT-S equal to KV over tau Vs plus 1. Yeah. So the other elements, remember there are in total there are 5 elements. So the third one, the composition sensor transmitter analyzer. Here we assume that the dynamic behavior of the composition sensor transmitter can be approximated by a first order transfer function. But tau m is small, so it can be neglected. So we have Km given by x dash ms over x dash s equal to Km, and the controller, the element that suppose that an electronics proportional plus integral controller is used. So we have learned about PID, proportional, integral, and derivative. So in this case, if you apply the PI, proportional plus integral controller is used. Then we have P dash S over ES equal to KC times 1 plus 1 over 2 S. Yeah? So in this case, where P dash S and ES are the Laplace transforms of the controller output, small p dash t, and the error signal EP, and Kc is dimensionless. Yeah, the gain, yeah? The transfer function gain. Okay. Kc is dimensionless. Yeah? So in this case, we have for the valve, we have this the control block diagram for the valve. There is P dash Ts given by Kv over tau Vs plus 1. So given you the mass flow rate of W dash 2s of kilogram per minute. Yeah? And for this one here, we have if we combine, there is the block diagram for the entire blending process compositions control systems. We have for the mass fraction coming here, coming in, and then the error here. For the first uh, controller here, and then the second one, and the third one, and the fourth one, and the fifth one here. Yeah? So all and also the feedback is coming with another transfer function here. So you can see how you can count how many they have. 1, 2, 3, 4, 5, 6, 7 here. Yeah. I mean the input and output 2. So the element inside is a 5 altogether. Yeah? So in this case, if you look at for those in, known as the sum that they're coming in here, A and B, we say C equal to A plus B. Yeah, we're talking about the transfer functions. Yeah, the transfer function C given by A plus B. For comparator, yeah, that is A, they're going to C, but it's a error of B. Then you can say C equal to A minus B. Yeah, so, yeah, because this is minus, it's positive, so C equal to A minus B. For block, we say the input xs coming into the function vs given you ys. So in this case, ys is equal to vs multiplied by xs. Yeah. So consider as a which is also considered as blocks in series. Yeah. So in this case, x1 will be g1s over x2 will be another transfer function p2s giving you 1. Yeah? And this can be simplified further to be equivalent to x1 as g1s multiplied by g2s giving you y. So this is y. Okay? So we look to step by step here. Yeah? So that's ending up. You can clean up. So from this one here, we clean up by on looking at the transfer functions here, become like this. Yeah? So the become a standard block diagram of a feedback control system. Yeah, we have a y set point, km, y set point, a plus, and a minus E, the error, GCP, GB, that's commodity, GP, and YU out. And here, the plus in Y here. Yeah? And the feedback went back here, PM and YM coming back here. Okay? So this is the standard block diagram for this particular stirred blending tank. So in the closed loop transfer functions, yeah, basically indicate dynamic behavior of the controlled process, yeah, or the process plus controller, transmitter, valve, etc. So it's now in the diagram, block diagram, we see 5 elements for controlling the process. Yeah. So this 5 element include the controller, the transmitter, and the valve, etc. Yeah. And the set point changes are the several problems in the case. If we assume the YSP not equal to 0 and D equal to 0, there is the set point change while disturbance change is 0. And YS about YSPS equal to that particular equation Km GT GV GT over 1 plus D3 GV GT PM. Yeah? It's for set point changes. For disturbance changes, there is the regulator, also known as the regulator problem. Yeah? Disturbance for disturbance changes. Remember the set point changes is considered a solver problem. Yeah? Whereas for disturbance changes is considered a regulator problem. Yeah? If we assume v not equal to 0 and y set point also equal to 0 for constant set point, then in this case we have ys over ds equal to gd over 1 plus dc dv dt dm. Yeah? And we can see that for y over d and y over y as t, yeah, equation 11.29 and 11.26 here, you can see that they have the same denominator, yeah, which is at the bottom here. One here and this one here. So in this case, if we can even make it even further, for example, the output of our previous system become the input of the next system, yeah, the integrated system, we ending up with another one from only GM here become GM2 and become GM1, for example, getting bigger and bigger. We can increase this further. Yeah. So this is considered as complex control system. Yeah. So just now initially we just consider this one here. Yeah. This one here. Then we add another loop here. That become like a double of what we had before. Yeah. But from what we have learned and what we have observed just now, we can say that the transfer function can be made as one, yeah, either in by adding a summations, either by summer, comparator, and block. So block in series and equivalence. Yeah? So that's the idea. So from this one here, become this one here, and this one here. You add another one, it become this one here. And of course, there should be not a problem if you put another one here. Yeah. From GM2, GM1, and into GM3, etc. Yeah, or 4, etc. This is this is what it means if we put something like this. Now become the graph here. We have another comparator here, for example. It's a direct straight. We have another one here. If we can give GQ3, for example. Yeah, this is an example. So for level in this case, it can be something like this. The block diagram for level control system. So for example, so instead of flow, we look into the level, and we can have something like this. Yeah. And for the step response for proportional control or the set point change, which is what it looks like. If you change the set point by a value of h, yeah, so it can be offset that much, for example. Yeah, based on what is the changes in the set point, yeah, the set point change. And if you have more set points changes, yeah, you can see here for different gain KC from 1, 2, and 5. You can see that what you can observe actually this is top here the limit of 1. Yeah, so if KC is 5 is bigger, the constant gain is bigger. The constant gain is bigger. It will be at the top here. Yeah, but if it become lower, smaller value, you can see that for KC equal to 2, but that step. Yeah? And for KC equal to 1 is something like that. So this is the step response. For step response. Yeah? So the constant gain will be something like this. Yeah. And for disturbance response, yeah. If for 5 we have it here. For KC2 is somewhere here, the middle, and for KC1 at the top. Yeah. So if before we look into the set point responses, as a k value increase, it will increase. Yeah. Towards 1. But for disturbance, when x is increased, it is reduced. This is the disturbance response in this case. Yeah. So if you look in more examples, for example, the proportional integral control of liquid level, like this one here, where we have the h, the height here, Q1 coming in and Q2 coming in, and the Q3 coming out. Yeah, we want to control H in this case, where the label transmitter and also label controller here together with the valve. Yeah, and for this particular system, then the block diagram will be given as this one here. YSTKM, Y bar ST to the plus here, so minus the GM here, the feedback, the error E, the DCP, GB, GP, and GB for the controller here. Okay? And you have a feedback GM. So for this system, you might for us in any engineering problems, you can assume a few things. First, you can say that for Q1 varies with time, and Q2 is constant, and constant the CP and the X sectional area of the tank A, and Q3 not the functions of the height H for uncontrolled process, and the transmitter and control valve have negligible dynamics compared with dynamics of the tank. Yeah? So in this case, the ideal proportional integral controller is used for direct acting. And for these assumptions, the transfer functions are given as VCS is equal to minus KC times 1 over tau IS. Yeah? And GVS equal to KV, GPS equal to 1 over AS, VLS equal to 1 over AS, and for KC bigger than 0. And GMS equal to KM. Yeah? Based on this system. So in this case, the closed loop transfer function is given by this one here is y over d equal to h asterisk of h dash over q1 dash equal to gl over 1 plus vc dv dpgm. And the previous we learned, which is this one here, this two here, 11.26 and 11.29 here. And by substitute y over d equal to 1 over as plus 1 minus kc times 1 plus 1 over tau is and kb minus 1 over as km. And simplified, we have y over d given as tau is over a tau is square plus kc kb km tau is plus kc kb km. Yeah? And the characteristic equation, which is this one here, the bottom here, and the denominator. Yeah, so a tau is square plus kc times kb km tau is plus kc kp km equal to 0. Yeah, and by recalling the standard second order transfer functions, the transfer function will be s given by k over tau square s square plus 2 lambda tau s plus 1. Yeah? And to replace this equation 4 here, this one here, in the same form as the denominator of the transfer function in equation 5, yeah, this one here, then divide by kc kb km, we have a tau I over kc kb km s squared plus tau I s plus 1 equal to 0. Comparing coefficients 5 and 6, we give you tau square equal to a tau I over kc kb km. So the tau is the square root of this term here, a tau I over kc. And 2 lambda tau is equal to tau I, so lambda given by tau I over 2 tau for 0 less than lambda less than 1. And by substituting, we have lambda equal to 1 over 2 square root of kc kb km tau I over a. And for 0 less lambda between 0 and 1, the closed loop response is oscillatory, and therefore it decreases degree of oscillations by increasing kc or tau I for constant kb, km, and a. So in this case, it can be considered as an unusual property of proportional integral control of integrating system. Yeah, the proportional integral control of integrating system. Yeah. So we have closed loop 1, closed loop 2, even closed loop 3 or 4 or even more. Yeah. So what's the integrating system? So in this case, we can say that we better off to use P only, yeah, the proportional only. So in this case, now we look into the issue of stability of closed loop control system. Yeah, the stability of closed loop control system. So in this case, if you look back the standard block diagram of our feedback control systems, yeah, the KM, YST, KM, and steady set point of Y bar us from ym here, the feedback letter from all systems here, ym giving you minus e, so gcp plus gvu gp yu here. Yeah, this is the standard block diagram of our feedback control systems. Then for proportional part only, the proportional control of the first order process, then the set point y over ys equal to this equation here. Between kc, kv, kp, km over tau s plus 1 over 1 plus kc, kv, kp, km over tau s plus 1. This term is given by the previous one. Yeah. And Gp equal to Kp over tau s plus 1. And Gv, Gc, and Gm are constant gain. Yeah. So in this case, K1 equal to K omega L over 1 plus K O L. And tau1 is tau over 1 plus K O L. Yeah. So in this case, K O L is actually Kc, Kv, Kp, and Km, which is this term here. So if we have a set point change given as m, yeah, set point change equal to m, then the functions y t, the function with respect to time y t equal to k1 m 1 minus e to power of minus t over so 1. Yeah? And the offset given by y st plus infinity minus y to infinity equal to m over 1 plus k o l. Okay? So this is for a tank example. Okay? And for the closed loop transfer function approach, we have y over y st to k kc over tau s plus 1 plus k kc and equal to this one here, which is 5 here. And the first order behavior closed loop time constant equal to tau over 1 plus k kc. Okay? So in this case, the first order, yeah, and a proportional, so you can say that it's a faster and depends only on kc, this one here. In this case, the effect of controller on closed loop response to a unit step in set point, yeah, given by this one here. So if kc is a big value of 15, for example, it will be near to 1. Okay, and then sorry, if kc is big 15, this one here, the big one here, so it become bigger and bigger. Yeah, but if kc is to 6, it will be going towards to the center. And if kc is small on 2, for example, it will be something like this. This is the effect of the controller gains on the closed loop response to a unit step change in set point. So when talking about stability, considering general stability criterion, we say here that most industrial processes are stable without feedback control. Yeah? And therefore, they are said to be open loop stable or self-regulating. And an open loop stable process will return to the original steady state after a transient disturbance. Yeah? the one that is not sustained to occurs. So for contrast, there are a few processes such as exothermic chemical reactors that can be open loop unstable. So we define stability as an unconstrained linear system is said to be stable if the output response is bounded for all bounded inputs. So otherwise it is said to be unstable. So now we look into the effect of um, proportional integral and derivative control or PID control on a disturbance change. So for a regulator, the disturbance change, so disturbance considered to be regulated. So for regulator where there are disturbance change exists, we want the disturbance effects to attenuate when control is applied. Yeah. So if we consider the closed loop transfer function for proportional control of a third order systems for the disturbance change, then the ys equal to 8 over s cubed plus 6s squared plus 12s plus 8 plus 8 kc ds. Yeah. In this case, we still consider the s as unspecified. Yeah. And gv equal to 1, gm equal to 1, and gp equal to gb equal to 8 over s plus 2 cube. And kc is the controller function. Or i.e. we see s equal to kc. Yes. So if we let tau s equal to s cubed plus 6s squared plus 2s plus 8 plus 8 kc, and if kc equal to 1, then tau s becomes s plus 4 times s squared plus 2s plus 4. So that's equal to s squared s plus 4 times s plus 1 plus square root 3j times s plus 1 minus square root 3j. So this is the real and immediate part. So in this case, it's a negative part. So since all of the factors are positive, in this case 1 over s plus a equal to e power minus at, and the step response will be the sum of negative exponentials, but will nevertheless exhibit oscillation. Yeah. And if kc equal to 8, then tau s equal to s cubed plus m s squared plus 12s plus 72, and that is actually equal to s plus 6 times s squared plus 12. And correspondence to sine wave for undamped, and this is the case of considered as a marginally stable. Yeah. But if kc is bigger than equal to 27, so we move from 8 to 27, then tau s equal to s cubed by default by here, s cubed plus 6s squared plus 4s plus 224 in this case. And given you the value of s equal to s plus 8 times s minus 1 plus 3 times the value of 3j, s minus 1 minus 3 square root 3j here. And the sign of the real part of the root is negative. And we obtain a positive exponential for the response. And the inverse transformation shows how the controller gain affects the roots of the system. Yeah? And the offset with proportional control for the disturbance step response, there is ds equal to 1 over s, then we have ys equal to 8 over system here, s cubed plus 6s squared plus 2s plus 8 plus 8 kc times 1 over s, and for y where t equals infinity to the limit of s to 0, s by s equal to 8 over 8 plus 8 kc equal to 1 over 1 plus kc. So therefore, if kc is made very large, from from 1 to 8 and then to 27, so we consider as a large, then yt approaches 0 but does not equal 0, and there is some offset with proportional control, and it can be rather large when large values of kc create instability. So in this case, the integral control for T equals to Kc over tau I integration from 0 to T e T of T dash dt dash, and Ps equal to Kc over tau Is times Es, and Gcs equal to Kc over tau Is. Yeah. So for a unit step load change, and Kc equal to 1, then Ys equal to 8s over s times s plus 2 cube plus 8 over so I dot 1 over s, and limit for s towards 0, giving you s by s equal to 0 equal to y towards infinity or with no offset, and it is uh, a fourth order polynomial. So that's a fourth order polynomial. Yeah. And for PI control, the GCS equal to KC times 1 plus 1 over 2 I s, then Ys equal to 8s over this term here, s times s plus 2 cube plus 8 kc over 2 I plus 8 kcs times 1 over s, yeah, with the limit of s to 0, s by s equal to 0 with no offset. And we adjust kc and tau I to obtain satisfactory response in terms of roots of the equation, which in this case is the fourth order. Yeah. And the PID control, there is the pure PID. We have GCS equal to Kc times 1 plus 1 over 2 Is plus tau ds. Yeah. So with no offset, and adjust Kc, tau I, and tau d to obtain satisfactory result, which requires solving for roots of fourth order characteristics equations. Then analysis of roots of characteristics equation is one way to analyze controller behavior. So we have 1 plus Dc times dv dp dm equal to 0. Yeah. As a rule of thumb, you can say that the closed loop response becomes less oscillatory and more stable by decreasing Kc or increasing tau I. Yeah. So for general stability criterion, considering the characteristic equation, that is 1 plus Dc dv dt dm equal to 0, noting that the left hand side is merely the denominator of the closed loop transfer function. Yeah. This one here, this is the denominator. Then the roots or the poles or the characteristic equations as to Pi, you determine the type of response that occurs. For example, for complex roots, then we have the oscillatory response. For all real roots, no oscillations. Yeah? And all roots in the left half of the complex plane is actually giving you a stable system. So for real and imaginary, for this part on the left is stable region, but on this one here, it can be increasing unstable region. Yes. So for if you look in more detail for the real part and imaginary part on the top, the y-axis is the imaginary part and the x-axis is the real part. All region in the left is stable region, both on the top and the bottom, and all on the right is actually the unstable region. Unstable region. Yeah? So this is the stability regions in the complex plane of roots for roots of the characteristic equation. For stability considerations, yeah, if you consider the feedback control that can result in oscillatory or even unstable closed loop responses, yeah, and we look also the typical behavior for different values of controller gain Kc. So that's the two things we will look into. For there is for stability consideration, whether the feedback control can result in oscillatory or unstable response, or of typical behavior for different values of control again Kc. So for roots of 1 plus Tc dv dt m, yeah, for auxiliary part and real part, and y-axis the auxiliary part and x-axis the real part. Okay. The first one here with um, the real with the negative real roots like this, positive real roots, complex roots with negative real parts, and also the complex roots for positive real parts. That's how it looks like. Yeah, so this is considered as the contributions of characteristics equations roots to closed loop response. And for root locus diagram for third order system, it's here the X denote an open loop pole and dots. This one is the asterisk here, not the open loop pole. Whereas the dots denote the location of the closed loop poles for different values of Kc. Then in this case, the arrow indicates change of pole locations as Kc increases. Yeah. So the GOL S equal to 2 Kc over S plus 1, S plus 2, and S plus 3. And that actually leads us to what's so-called the roof stability criterion. Yeah. What actually means the roof stability criterion? First of all, we look into the characteristic equations. You have a equation of an Sn plus an minus 1 Sn minus 1 to the a1s plus a naught equal to 0, yeah, where an bigger than 0, and according to the roof criterion, if any of the coefficients a naught, a1, and an minus 1 are negative or 0, then at least one root of the characteristic equation lies in the um, in this right hand side of the equation, yeah? And therefore the system is unstable. Okay? And on the other hand, if all of the coefficients are positive, then one must construct the roof array. What's the meaning of roof array? We look here, next slide. So the roof array, we have row 1, 2, 3, and 4. So an to n minus 1, an minus 2, n minus 4. So next follow the n minus 1. So the next one, an minus 3, n minus 5. So we have b1, b2, b3. So c1, c2, c3, so on, so forth. So the a, b, c, d, so on and so forth. Yeah, until the n plus 1. Yeah. So in this case, for the so-called the roof array, yeah, for stability, all elements in the first column must be positive. This one here. The first column must be positive. And the first two rows of the roof array are comprised of the coefficients in the characteristic equation. And the elements in the remaining rows are calculated from coefficients by using the formula here, b1 equal to this one here, b2, b1, b2, etc. Yeah? And the n plus 1 rows must be constructed, and the n is the order of the characteristics equation. And how we apply the roof array. So the application of the roof array in this case given by this one here, there is Gp equal to Gl equal to 8 over S plus 2 cubed, where Gv equal to Gm equal to 1, Vc equal to Kc, and the characteristic equation is 1 plus Vc, Gv, Gp, and Gm equal to 0. And in this case, 1 plus 8 Kc over S plus 2 cubed equal to 0. So the S plus 2 cubed plus 8 Kc equal to 0. Yeah? And simplify it, we have S3 plus 6 S squared plus 12S plus 8 plus 8 Kc equal to 0. And if we want to know what the value of Kc cause instability, or at least one root of the above equation is positive, then by using the roof array, we have 1, 12, and n equal to 3, and then 6, 8 plus 8 Kc here, and 6 times 12 minus 1, 8 plus 8 Kc, 0, and this over 6, and 8 plus 8 Kc to 0. And for condition for stability, we say that 72 minus 8 plus 8 Kc becomes 0 for Kc less than 8. and 8 plus 8 Kc equal to 0 for Kc bigger than minus 1. So in this case, the important constraint is Kc less than 8, and for any Kc bigger or equal to 8, it will cause instability. Yeah? So this is, in summary, the flowchart for performing stability analysis with a root criteria. First, we need to look at the process model, which is non-linear or linear. If it normally, of course, it's a non-linear. So even if it's non-linear, then we need to linearize it. Yeah. If we um, uh, cannot linearize it, then we can apply the stability test for non-linear system. And if we can linearize it, we can obtain the transfer functions model. From there, we can uh, have the model that contains time delays. If yes, then continue to approximate it. If not, then go applying roof stability criteria. And if it contain time delays and you can approximate it, you can also go back to the roof stability criteria. If not, then we can substitute S equal to J omega or apply frequency response stability criteria, which is in the next chapter 14, which we will not cover for this course. So this is the first chart for performing a stability analysis, where the roof stability criteria will be considered. And there are additional stability criteria on top of roof stability criteria. You can also have the board stability criteria, which we discussed in chapter 14, but we will not go to chapter 14, only up to chapter 11. And also the NICE stability criteria. So another two criteria on top of the roof stability criteria, we also have the board and also NICE stability criteria. Any questions? You can see the beauty of using the matrix, the transfer function. There we can um, be able to analyze a complex control systems, complex and integrated control system. Okay. If you're this, if you're dizzy already, yeah. So that is actually conclude our um, lecture on dynamic behavior of closed loop control systems. Any questions? Okay. Maybe you can look into these systems again on how, for example, you can look on how the um, block diagram for figure computer system being designed for this particular systems of state bending system, yeah, and how they have analyzed from point to point here to come out with the transfer function for each. Yeah. We look into, for example, the current to pressure transducer, the element inside the feedback control systems, yeah, control valve, composition, sensor, transmitter, controller, etc. Yeah, so something like this, the complex one. And this point here, you need to know the summer, compressor, and the block. Yeah? So we can simplify it to this one here. Yeah? And if you want to make it more complex, get another one here. Yeah. Uh, this is one the system where we have more here. Yeah. Okay. And what the effect of K? What the effect of so etc. to the system. Yeah. And from there we move to the definition of stability. Yeah. defect or disturbance change, and then the difference between integral, PI, and PID controller. Yeah, leading to the stability criterion and the notes on the roof stability criterion. One of the criterion that we consider the roof stability criterion. Yeah? And we will consider roof only. And this is the flowchart for performing the stability analysis and other stability criteria like body stability criterion and Nyquist stability criterion will be in advanced topic on control system, which we will not consider yet in this lecture. Yeah. Okay. So no questions. Any questions at all? If not, then I can close this one. We'll go back to this ellipse thing. Yeah. Okay, for your information, we don't have any group presentations. Yeah. So for next week, I will we don't have any group presentation. Now it's week 11, so next is 12. 14 year exam, so we have 2 more weeks. So for next week, we'll discuss on the CS design, yeah? The control system design, which presentations will replace your group presentation. So I will discuss on CS control system design on this Friday, not next week. Yeah? But this Friday, before we start on the control system design, you can ask me questions if you want with regards to your assignment before you submit your assignment. Yeah? No question? Sorry, 3 o'clock. You can call it a day, and we continue again on Friday. Okay. So if you um, can continue to take your attendance while you can also ask me questions if you have any questions. You can leave if you don't have any questions, but if you have any questions, you can ask. I can stay here until 3:10.
Okay, bro.
Okay, welcome.